Hi, I'm Pablo Pintabona. Just to clarify, I'm not a mathematician, but rather a math enthusiast with an undergraduate degree in economics. All the work, tools, statements, and conclusions you'll encounter here are my own, unless otherwise specified. Although Spanish is my first language, I'm sharing this in English to reach a broader audience. If you speak Spanish, you can use YouTube's closed caption tool to follow along. In all previous video series, we have extensively used Fermat's little theorem without ever presenting its proof. This new set of videos aims to address that. Interestingly, we can offer an infinite descent proof, a technique developed and widely used by the French mathematician in his investigations. So this proof could be Fermat's. And as Euler-Totient's function is an extension of Fermat's little theorem, we can also ascertain its validity making use of the infinite descent technique, plus Fermat's theorem. As with the previous sets of videos, we are dedicated to making these concepts accessible to beginners. No convoluted mathematical jargon will be used here. While subtle techniques are indispensable for unlocking profound insight into numbers, they can often overshadow the joy of using simpler tools. Let's take a moment to appreciate the basics and show how they, too, can lead to remarkable results in problem solving. This presentation is structured into 3 sections. In the first section, we will explain why Fermat's little theorem is a key concept in number theory and offer a proof using the infinite descent method. In the second section, we'll delve into Euler's Totient function, its uses, and provide a detailed proof by infinite descent as well. In the third and final section, we'll focus on a specific point from the demonstration in the second section that needs more clarification, introducing a function similar to Legendre's formula. Fermat's little theorem states that if p is a prime number and a is an integer not divisible by p, then a raised to p minus 1 is divisible by p. Fermat's little theorem is one of the most fundamental properties of the arithmetic of whole numbers, with wide-ranging applications in various fields of mathematics and computer science. It plays a crucial role in numerous mathematical proofs, helping to establish properties and relationships within various mathematical structures. It is a cornerstone in modular arithmetic, providing a powerful tool to solve congruencies and understand the properties of modular arithmetic. It provides a quick and simple primality test. It is utilized in various cryptographic algorithms, such as the RSA algorithm, which is widely used for secure communication over the Internet. And it is used in the generation of pseudo-random numbers, which are essential in simulation, statistical sampling, and various other computational tasks. As an intro, before offering a proof, let's have a brief exploration into the origins of Fermat's little theorem, which interconnects luminaries such as Euclid, Fermat, Euler, and Lagrange. Fermat's little theorem is named after the French mathematician Pierre de Fermat, who stated it in a letter to his friend Marin Mersenne in 1640. Fermat came to discover this particular divisibility rule while studying perfect numbers, those numbers that are equal to the sum of its divisors. For example, 6 equals 1 times 2 times 3 equals 1 plus 2 plus 3. Euclid, around 300 BC, already had proved that the formula 2 raised to n minus 1 times 2 raised to n minus 1 yields perfect numbers when 2 raised to n minus 1 is a prime number. It was through investigating for which values of n is 2 raised to n minus 1 prime, a Mersenne prime, that Fermat discovered the basic property of whole numbers that is now known as Fermat's little theorem. As usual, Fermat declined to offer a written proof of his theorem. It wasn't until nearly a century later that Leonhard Euler stepped in, providing a published proof of it. Euler's proof relies on the concept of Euler's Totient function, which counts the number of positive integers less than a given integer that are relatively prime to it. Fermat's little theorem happens to be a special case of Euler's Totient function. Fermat originally stated his theorem as a raised to p minus a is divisible by p when p is prime. Thus, a raised to p minus 1 is divisible by p when a is an integer not divisible by p. In order to proceed with the proof by infinite descent, we first need to introduce the binomial theorem, where the integer coefficients are the binomial coefficients, where k factorial is the factorial function for k. Note that when n equals p, then all values of I factorial times p minus I factorial don't have p as a factor, as I is smaller than p, bigger than 0. So binomial p choose I is divisible by p when given that condition. Thus, we are taking aside the cases when I equals 0 and I equals p. So by inspecting the binomial theorem, we conclude that p divides x minus y raised to p minus x raised to p minus y raised to p. Before we kickstart the infinite descent, we only need to note two trivial results, that p divides p raised to p minus p, and that 1 raised to p equals 1. We can now proceed with the infinite descent. Please follow the steps. First, we already know that p divides the terms on the left side of the equation. Next, we replace 1 raised to p with 1, the trivial result we mentioned earlier. Then, we add and subtract p, regrouping the terms to obtain p raised to p minus p, which we already know is divisible by p. Therefore, the remaining terms on the right side of the equation must also be divisible by p. Consequently, we conclude that p divides p minus 1 raised to p minus p minus 1. While this deduction may seem excessive for a result we already know, repeating this process in the subsequent steps will effectively demonstrate how the infinite descent works. In the second step, we start this time using p minus 1 for x and 1 for y. So p minus 2 raised to p minus the difference of p minus 1 raised to p and 1 is divisible by p. Next, we replace 1 raised to p with 1, and then add and subtract p minus 1. Finally, we regroup so as to use the result obtained in step 1. P minus 1 raised to p minus p minus 1 is divisible by p. Thus, the remaining terms on the right side of the equation must also be divisible by p. That is, p divides p minus 2 raised to p minus p minus 2. So here we can see how the infinite descent starts to display. So we continue with the steps, making x increasingly smaller until we reach 1, the smallest positive integer. At this point, we conclude that 1 raised to p minus 1 is divisible by p. And that's true, as 0 is divisible by any integer. Once proven that p divides r sub I raised to p minus r sub I, then it follows that p divides p times k plus r sub I raised to p minus p times k plus r sub I, for k equal or bigger than 0. Let's now illustrate the proof with an example. P equals 7. Please follow the steps. As the infinite descent works for all integers r sub I equal or bigger than 1 and equal or smaller than 7, then it worked too for 7 times k plus r sub I raised to 7 minus 7 times k plus r sub I. In conclusion, Fermat's little theorem is one of the most fundamental tools of number theory, with applications that span across diverse areas in mathematics and computer science. Proving it by the method of infinite descent just requires the use of the binomial theorem, plus assuming some trivial results, that p divides p raised to p minus p, and 1 raised to p equals 1. This proof aligns closely with what Fermat most likely discovered, though he did not formally document his findings. Leonhard Euler provided the first written proof of Fermat's little theorem in 1742 using the binomial theorem and an induction method. In 1750, he extended Fermat's theorem by introducing Euler's Totient function, which will be explored in the next section. We will demonstrate how this can also be proved through the method of infinite descent.